All right, hello and welcome to my presentation for my artificial intelligence project, which I titled Virtual Mobile Robot, creating a robot simulation that can navigate room space, retrieving packages, and placing them in a repository bin. Here's an outline of our presentation today. I'm going to be going over the objectives of the project, some background information about why I chose this project, some of the methods that I implemented, some of the challenges along the way, and lessons that I learned. Alright, so first objectives. The primary objective of this project was to bring together all or many of the things I learned in college in computer science, which includes robotics, artificial intelligence, and some other things that I'll go over in a second. And I wanted to bring them all together into one interesting project, something that interested me, and that ended up being a robot in a simulated 3D space that can navigate and make decisions about its behavior toward a certain goal. So here are some of the courses, along with a hobby of mine, that all kind of came together to create this project. So we got artificial intelligence, mobile robotics, data structures and algorithms, trigonometry and other math courses, finite automata, and game engines, which has been a hobby of mine for a few years. Secondary objectives were to learn how to write C# code and how to use the Unity game engine. I also wanted to apply robotics knowledge from my robotics course and to apply algorithms that I learned in school. So now moving on to some of the background of this project. I love Sand State's mobile robotics course, but it was very theoretical with not a lot of visual implementations of the things that we were working on. So I wanted to apply that knowledge and create something that could visually demonstrate some of the things that I learned. Also, the A-star algorithm. So this is one of my favorite algorithms that we've learned. It's a pathfinding algorithm, and it has many practical applications in the real world, including robotics, video games, navigation and GPS, networking and communication, and operations research. So it's a great algorithm to know, and I wanted to kind of solidify my understanding of that by putting it into practice. So moving on to the next section, which is the method. So for mobility, I wanted to give this robot a very limited set of physical movements, and that only includes two things really: accelerate forwards and rotate. So it can rotate in either direction and it can accelerate. So it's really only two values that can be manipulated by the robot itself. And here are a couple of functions that carry that out. So here we have move forward, very simple. We're just taking the transform position of the robot and moving it forward by a certain speed. And then a little bit more sophisticated here, we have this manage targets function, which is basically going to look at a list of targets and grab the top one on the list, and we're going to see, are we at this target yet? If not, then we're going to check out the distance, and once we reach that target, we will remove that target from the list, and that will bring the next target to the top of the list. So with this technique, you can queue up multiple targets, and this will come in handy for pathfinding later on. Over here we have this function, which is to add a target, and then this function, which is to clear targets, to clear all targets, and this is good for debugging as well as if the robot gets stuck on its current path, if something goes wrong. All right, for rotation, so we've got this rotate bot function, very simple. We're just gonna basically add a value to its rotation vector, and we're fixing its vertical rotation upwards. So even though we're in a 3D environment, we're not really worrying about this kind of rotation. We're only really worrying about this kind of rotation. And that simplifies the pathfinding for this simulation. And then we have this other helper function, which is called rotate2, which allows the robot to rotate towards a certain target point. So if we want to face our target, say we need to move to a box, we can rotate to that point if we know that point. And so that's very useful as well. Now moving on to actions. We really only have 3 non-movement actions for the robot, which are pick up, drop off, and sense. We'll cover sense in a little bit. Right now we're mainly going to cover pick up and drop off because they're simple, but the actual implementation is not quite so simple. We'll go over that in a second. So to pick up a box, we need to have a box in the room with us within a certain range, and we will position ourselves facing the box, and we have to turn off collisions between the robot and the box. Unity has a whole collision system built in for games, and we are using that to simulate solid collisions, so that if the robot walks into a wall, it'll stop at the wall. If the robot walks into a box, it'll bump into the box. And when it's carrying the box, we want to disable that because it's just a very simple state of the box is kind of pinned to the robot's arms. So we disable these collisions. We parent the box to a mount point, which is on top of the robot's head, as you can see in the image. And so while the robot is carrying a box, this box object is just going to be pinned to its head. So now for mapping. So this was probably the most interesting part to me of the project, and took a lot of thinking and planning. But basically, we're going to start by creating a 50 by 50 grid. The size is pretty arbitrary. That's just the size of this room, but it could really be any size. It could be infinite as well. But just to keep it simple for this project, I chose a 50 by 50 grid. And the data structure that I chose for this grid is a dictionary, which is like a data structure that has key value pairs as its elements. So the key, we're looking up coordinates as our key, and our values are going to be these cell objects, which is a class that I created, which has certain data in it that the robot needs in order to do its planning. So the key in the key value pair is a coordinate. It's a vector 2 integer. So 0, 0 would be one element's key. 0, 1 would be another element's key. And each of those keys contain a value, which is a cell object. And a cell has a property called a cell state, which can be an obstacle, it could be a box, it could be a free space, it could be unknown. And at the very beginning, every single cell is of type unknown because the robot hasn't sensed anything yet, so it's in a completely unknown environment. And we gain more information about our grid through sensing. Everything is learned through this sensing function, which I'm going to cover next. Here is a screenshot of what the grid looks like when visualized. So As you can see here, we've got a grid of cubes. The red cubes are ones that we sensed and decided were obstacle spaces. And as you can kind of make out here, they are wrapped around the walls here. And then the green boxes are where boxes are, cardboard boxes, which are like our target items, you know? So those are going to be green. So the robot is going to want to grab those and put them at the yellow boxes, which are the bins. And then the black squares are unknown. And then these really faint blue squares are free spaces. So this is like walkable space that the robot can traverse. So basically the robot is never going to plan a path through obstacles or through unknown space. It's only going to path through free walkable space, and it's going to walk towards green cells. Here is just a small sample of some of the code that has to do with mapping. So here we have this class W grid, which is the world grid, which is this whole map I've been talking about. So these are some of the substructures within it. So we've got an enum cell state, which has those states I was just talking about. And then we've got all these mostly helper functions, search body. So this is if we need to do a linear search through the grid, which comes up quite a bit. We got find nearest, where we give it a position and find the nearest of a certain type of cell. We have unknown neighbor count, which is used in pathfinding, which counts the number of unknown neighbors of a given cell. We have choose random cell, which is used in exploration. We have get or create and set or create cell, which are very important in anytime we need to change a cell state or learn about a cell state, receive a cell state's information, or when we're first building the grid in the first place. Very important fundamental more really fundamental methods here that get used a lot are grid to world and world to grid, which is kind of a unity thing in that it converts unity coordinate positions in the room in the Unity engine to our grid system. And that's very important for anything that involves physics, like moving or getting the actual real locations of things in the Unity environment. So now for sensing, so I wanted to simulate LIDAR, and LIDAR is what a lot of robots use, where they kind of point a laser out, and when the laser bounces off of a surface, we get that distance, and by calculating that distance, we can kind of formulate our environment. So we can figure out how far away things are, where things are positioned, whether or not anything is moved, etc. And to do that, I used a raycast, which is kind of like a cone. It's used in video game development a lot. It's pretty similar to LIDAR. It just shoots a ray out from a point, and then when it hits a certain type of object that you define, you get back data about that object, like how far away is it, which object is it, etc. So I use that to simulate LIDAR, basically. And I only gave the robot one because I wanted to I kind of wanted it to be challenging for the robot, to actually have to build a model of its environment. So it only has one sensor that just pokes out through the front, and so if it wants to see what's behind it, it has to turn around, And here's just a little graphic about ray casting that I found. So we've got the ray origin, it's got a direction and a distance, and then where this exclamation point is, it's hitting a surface, and so we can get data back about that surface. And here are some of the functions involved in sensing. So here we send out this raycast, and we're looking for obstacle objects on the obstacle layer. And basically, if we get a hit, like if we hit a wall or an object, then we get that object back, and we get some information about it. And then what we do is we do a little bit of math here on the right with this mark free cells function over here on the right, and we basically walk along that ray and mark any cell that it's touching as free until the end when it hit that solid. So this is how it kind of creates its map. All right, so pathfinding. This was probably the most complex thing to program, but very important and not all that complex. So we're doing an A-star algorithm over the grid, and the goal cell will be dynamically assigned based on sensor data. As you can see in this image, the green line with the dots is the path that was decided on by the algorithm. So with the A-star algorithm, basically the way it works is we have a score of kind of cost going from cell to cell, cost of 10 to go straight up or down or left or right, and a cost of 14 going diagonally. And so we have a start and end cell that are known, and then we've got two lists, an open list and a closed list, and we are going to loop until the open list is empty, basically calculating the cost of each cell, going from our starting cell to that cell, and then checking out its neighbors. And if any of the neighbors are either occupied or unknown, we just don't calculate that cost. And so the path never paths through those, and you end up with these nice optimal paths through the environment. And this is the equation. It's based on Dijkstra's algorithm, but it adds this heuristic, which is like an educated guess based on all the previous cells calculations. And now the control unit. So the control unit is like the overall planning center of the robot. It's where we execute all these functions that we've been talking about, in what order, when it does certain things, and it makes all these decisions based on checks. It also contains timer-based fail-safes in case the robot gets stuck, and we'll cover some of that too. So basically, it's pretty simple. This robot just has a small number of finite states: look for, move to, and ready action. And those can be broken up a little bit, but in the code, it's just one state. But you can either be looking for a box or looking for a bin based on if you have a box or not already. Same thing goes with move to and ready action. In this switch statement, we have a finite state machine. And the major requirement there is that we always know how we get out of that state and which states we go to from the previous state. So here's an example in ready action. We've got this next action variable. If the next action that we're supposed to do is pick up a box, then we try pick up nearest box. And once that's done, then we reset this init flag, and we queue up the next action to be no action, and we set the state to look for, because now that we have a box, we are going to start looking for a bin. We also have this method, exploration. So I had to think about, like, what does the robot do when it can't find a box? Because in this environment, as you'll see in the demo, there are walls and things where you can't see the entire room just by spinning around and looking. So the thing that I figured, and it's a little bit rudimentary, but the simplest thing I figured to do was to just find the nearest frontier, which is like where free space meets unknown space, and go to that frontier, and then do your sensing in a 360-degree rotation, and then you'll have new data. And if you still don't see anything, go to another frontier. Eventually the robot will explore the entire room. So here are some of the challenges that I faced in this project. Unity challenges. I have never used Unity much before beyond the simplest tutorials. So it was pretty overwhelming. There are a ton of features, and I pretty much didn't need to use any of them except for the most bare bones things. But the way that the program is designed is it's throwing all these features at you, and so I kind of had to navigate that, and that was really hard. Which is kind of a thing about programming, you know, especially with engines and big libraries and frameworks, is there's so much going on, and often you only need to use like 5% of it. So yeah. Design challenges. Like I said, making that map was pretty tricky at first. I know it seems simple now, but when I was starting just kind of from first principles, it was pretty mind-boggling on how I was going to do that. Coming up with the robot's knowledge representation was pretty challenging. Aesthetics. So I didn't want to concern myself too much with the, beautiful graphics or anything like that, as I'm not a 3D artist. However, one thing that I did definitely come up against was it's hard to even convey basic information sometimes without a little bit of aesthetic design. So I did have to make it look good enough to get my point across, basically. And some of the lessons, getting help, different methods of getting help, and going with the flow of design with computer science projects. So for tutorials, I find that they are good for discrete feature chunks. So like for A-star, a tutorial was great for that. I recommend this video for anyone that wants to learn A-star. It has a really good introduction and then a good code system in Unity for implementing it. However, if you did watch this, you would know, and then you looked at my code, you would see that they're quite different. And that goes into the second point, which is not to be afraid to modify or go off the trail of a tutorial, because sometimes the tutorial, it gives you the way to do things, and sometimes there's a better way to do it, but that tutorial will kind of get your foot in the door and help you with that. Documentation, obviously, a solid resource for anything, especially something like Unity. However, sometimes it can be a little bit verbose, or it won't have enough about something. And so that is where large language models come in. I find that they are good for two things on two extremes of a spectrum. I find that they're pretty good for big picture brainstorming and just kind of like throwing ideas out there, very big picture, and then really small picture, like how do I do this in Unity? Kind of like a documentation, but if you have a really kind of weird question that you can't just type into a documentation search bar. So really good for those two things. And then finally, just going with the flow. So when I was coming up with the map system, I kept thinking about the room as like a weirdly shaped grid, like not a perfect rectangle. And I realized that, a computer is always going to want to have a perfectly shaped rectangle. And I kind of realized that there's not really a difference between an oddly shaped grid and a rectangle with a bunch of unknown spaces on the edges. You know what I mean? So just little things like that, making the computer work for you by doing what it likes to do. So that and manual control. So the first thing that I did was implement a system where I can click and make the robot go exactly where I click to. And that got me going with all the controls I needed for the robot before it had its own brain, so to speak. I could kind of just control it manually. And implementing that first really helped me kind of get to know exactly what the robot does in order for it to plan its behaviors. So manual control first is a good one. And that's my talk. I will now throw it over to the demo presentation of the virtual mobile robot. Thank you very much.